So we've all heard about the call stack, but what is it and why is it so important? Let's look at a really basic program and we'll illustrate why it's so important. We're going to call a function called print hello, which is just going to print out hello world. Now, each of these instructions has a memory address. So what's really going to happen here is before we call print hello, the CPU is going to look at the next instruction. In this case, it's exit 0, and it's going to write down the address of that instruction, 40102A. We need somewhere to write this value so that we know what we were doing before we called that function. So let's say that we save it in the CPU, let's say register 15. Now we're free to jump to print hello because once we're done there, we know where we were before. So we can write hello world to the terminal, and then we reach this word here return. So what return is going to do is we're going to look back at that register, right, holding that return address, and we see that it's 40102A. So we jump back to that, and now we're right back to where we started. We're right after print hello. We're at that next instruction that was in line, and then we can continue executing. So that was a successful function call and return. Now let's add a second function call and see if anything changed and if our system holds up. So in this case, we're going to do what we did before. We're going to call print hello. So we write down the address 401069 for the next instruction that's after our function call. And then we open print hello. But now we have another function call within print hello. This is another nested function call. If we follow the same process, we see that there is another instruction ahead, address 40109B. So in this situation, we have to write it down in register 15, right? That's the standard procedure here. And we move on, we call print goodbye. We write goodbye to the terminal, and then we return. We look at R15, we see it's 40109B, so we jump back. This is fine so far. But this instruction now is to return again. So it's going to look at register 15 and see 40109B and return to that value. And it's a really strange sort of infinite loop here, but it is an infinite loop. We're going to continually return to the same instruction that wants to return over and over and over again. And we see that our system failed here because we're only able to keep one address in memory. So we're unable to make any sort of nested function calls. As soon as we make a function call from within a called function, we're completely out of luck. What we really need is a system where we can save as many return addresses as we need. So if we look at this next example here, let's do the same thing with a slight twist. We're going to allocate space in the RAM for as many memory addresses as we want. So if we're on a 64-bit system, that means that every memory address takes up 8 bytes. Let's say we want to be able to save 500 return addresses to make 500 nested function calls. Then we're going to need to get 500 times 8 is about 4,000. So about 4 kilobytes worth of memory space. And all they're going to be are just slots where we can write one address and then another address and another address, and we're never overwriting any of them. We could just keep going up sort of in a stack, which is why it's called the call stack. So now instead of using register 15 as a literal memory address where we're going to return to, what we're going to do is we're going to make it point to that first slot that we've allocated in our stack. So in this case, it's 402000. In this slot here, we can write an address. And then once we're done with that one, we can move upwards, go to the next row, we could say, by going up 8 bytes, and we can write the next address and go up and write the next one and so on. So let's look at this example here. We go into main, we call print hello, but before we do that, we see that the next instruction has the address 40101A. So again, instead of writing that directly to register 15, we're going to look at what's in register 15. And in this case, it's 402000. So we're going to go to our RAM and look up that address in memory. And then all we're going to do is write that memory address of exit of the next instruction into that slot. So 40101A is written to RAM at address 402000. And once we're done writing it, all we're going to do to R15 is we're going to increase it by 8 just to go to that next slot. So we've successfully written our first address to the first slot. Now we move to the second slot where we're ready to write another address if there's going to be one. And in our example, of course, there will be. Once we get into print hello here, and we write out print hello, we see that print goodbye is there. So we do the same thing as before. We look at the next instruction. Well, it's at address 40102F. So all we do is we look at R15 and we see that R15 contains the value 402008. So we go to our RAM, we ask him, hey, let's go to address 402008. Let's look at that memory cell. The RAM loaded up and we just paste in 40102F, and then we increment again R15 by 8. So now we're at 402010, and we're ready for the next address. So going back to the execution now, in print goodbye, we write goodbye, and then we return. So what happens here is we just go backwards. We look at R15 and we see that it's pointing to 402010, and we reduce it by 8 because we know it's at the next free slot, we could say, right? The next location that we could write to, but we don't want to write to it now. We want to read from it. So we subtract by 8, we just do the reverse, and we see at that slot, the address is 40102F. So we jump to that location, which takes us back to print hello. We can finish off that function, return, and then we see another return here. So what do? We look at R15, and we know it's at that first free slot now. So we subtract it by 8, and we see at 402000 is address 40101A. So we jump to that, which is that exit statement, that exit instruction in the original function. So the call stack is nothing more complicated than this. Originally, this is really what was needed, and this is why the call stack was made. Other features were added onto it where we can store local variables and stuff, but what we're going to do right now is actually build our own call stack in assembly to illustrate this. And then after that, we'll use the built-in stack with the CPU. But let's jump into the assembly and get started with our call stack here. If it's your first time joining me, go to x84.halb.it and then click launch the app, select GNU, and then you can copy and paste. I'm gonna have this code in the description. We have the start of our program, and we have our exit function here, and then we have our print hello function, and we have our print world function. And this example was from the previous video, so we could change this to print goodbye, and I'll just change this to goodbye. Okay, all better. So we're going to first save our return address. So we want to return here. The main program here is just what we saw before, but this is now in assembly. So we're going to jump to print hello, and then we're going to jump to exit. Print hello is going to go through its code, and then we're going to jump to print goodbye down here, and then we're going to jump back right to register 15, which is going to hold our return address, go back to resume hello. What we'd want to do is get back to start, but in this case we do have that infinite loop problem, and we can see that if we look here in the disassembly. We're going to jump down to print hello, then we're going to actually print out hello world. If you haven't seen that before, we tell the kernel that we want to write to the terminal by setting these registers. We tell it what text we want and how long the text is, and then we actually execute that command. And then after we're done with print hello, we're going to save our return address. So we're going to say that we want to return to resume hello. So we're going to tell print goodbye by saving it to register 15, which address we want to come back to. And then we jump down to print goodbye, we execute that code, and then we jump back to resume hello. But now we're stuck in an infinite loop. I'm pressing the forward button to continue executing. He's trying to jump to R15, expecting it to hold this address, but it really holds its own address, and we're just stuck here forever. So what we want to do is use the call stack. Let's just call it call stack. And we want to do .skip, and I'm going to put 4096, which is totally arbitrary, but I want mine to be able to go 500 function calls deep. So 500 times 8, because it's 8 bytes per address, equals 4000, and I'm just rounding it up to the nearest full kilobyte, so that's 4096 for 4 KB. And that's pretty much all we need to do on the RAM. We just need to make sure that we have this space available. Now, what we want to do in the very beginning is we actually want to load R15 to point to the start of our call stack. So in the very beginning, we're going to do load effective address R15, and we're just going to put call stack here. And if we run this and we step, now we can see that R15 402000 is the start of our call stack because we just loaded that label into R15. And we can prove that too. So over here in the stack, memory is pointing at the actual stack, which we will use at the end of this video. But for now, we're just going to treat this as a memory viewer, because the way that the playground works is wherever the stack is, it shows us a bit of a preview. So what I want to do is just do a very slight adjustment here. We're going to load to the stack pointer, which again, I don't want it to be confusing. We're not really using their stack, but we're going to use the feature that allows us to see the memory. So we're going to move the stack pointer to that location as well, so that we can see our empty space. So if we step, then now we can see we have all the empty space, and it starts at 402000, which is exactly where R15 points, and that's exactly where the call stack begins. Okay, and we can prove that this is ours, because if you put a comma right here, then you can default all of that data to be a certain byte. So let's say we want it to be FF. Then if we run this, so we've set R15 to point to that call stack, and then we're going to set our little memory viewer. Don't think of it as a stack at all. We're just using it to view our memory. We see now it's full of Fs, right? Because we've set all 500 quad words, I guess you could say, which 8 bytes is a quad word. It's all 4K of space, all 4 kilobytes has been set to FF just to prove that it's ours and we own it. We can change this if you want to some other random value here, and you can see that it does take that value. So let's zero it out to make it clean. And now we can get started. So we know that R15 points to the first slot here. This is going downwards because the memory is increasing downwards. 0, 0, 0, 8, 1, 0, 18, 20, 28. So our first slot is right here at the top. And now all we want to do is get any return address that we need and put it into our slots. And R15 is going to keep track of which slot we're on. So let's do that. We know that we're going to call print hello here. So before we call print hello, we want to make sure that we can resume after print hello is done. So let's load to REX as a temporary holder the address of resume here. Let's take a look at that, make sure it works. So we've loaded 40101A to REX, which is what we wanted. Here's REX, 40101A is resume here, perfect. And then all we want to do is use a move command and put R15 in brackets. Why do we put it in brackets? We don't want to move anything to R15 itself. When the move command is used with brackets, it looks inside R15 instead and sees the memory address, and then it will look it up in memory. So it won't look at R15's actual literal container. It will say, well, what is in R15? Well, right now it's 402000. So let's go look that up in memory, right? That's how we do that with the brackets. And we're just going to put the value at REX. And this one's not in brackets, so it's just going to take the literal value. So let's step. So we have now our address in REX, and we're going to shift it now into memory. And you can see it showed up here, 40101D. It looks like it's backwards because it's a format called little endian. Don't worry about that too much, but you can see the similarity, hopefully. We'll cover little endianness properly in a video all about what it is and why we use it. But for now, you'll see that it's stored there, 40101D. And now remember, R15 is still pointing to this first slot here, and we really want it to point to the next one, right? We want to, as a good practice, just make sure that anybody who needs to store their address doesn't need to worry about where R15 points to. We just always leave it pointing to the next free row. We could say the next free slot, the next free address. So we're going to very simply add to R15 the value of 8. Let's run through, update our memory, save our address to REX, send it to the RAM. And then we're going to increment, right? This is at 402000, still that first slot, increment by 8. And now we have 402008, slot number 2, right? This address is very safe. We're not even looking at it anymore. And we have our next slot available, our next empty slot. So now we're ready. We can jump to print hello. So let's scroll down. We tell the kernel that we want to write to the terminal. And then now we want to print goodbye. So before we print goodbye, of course, we need to know where we want to return to. Well, we want to return right here to resume hello, we could say. So what do we need to do? We need to save our address, right? So let's do the same thing that we did before. So we're going to load to REX, which is just a register that we're using to do some of our work, we could say, and then send it off to where it needs to go. And we're going to load this label's address here, resume hello, to REX. And then after that, we want to ship it off to the memory. So we're going to move with brackets, right? Whenever we write to memory, you put it in brackets. So R15 in brackets and the literal value of REX. So at this point in time, we should see it loaded to memory 40105C. And that's exactly this address here, which is great. That's what we want. And then we ship it off to memory and you see it's in that second slot. First one is perfectly fine. Second one looks good too, 40105C. And then now what we can do is jump to print goodbye. But first, of course, we want to keep our good programming practice here. At least for this program, we want to make sure R15 always points to an empty slot. So we add to R15 the value of 8. Let's run this again. We save our second address, ship it to memory, and then we're still pointing there 402008. So we step, and now we're pointing to 402010, the third slot. Everything looks in perfect shape. So now we can jump to print goodbye, and we can run print goodbye. And we have a literal jump here to R15. So this is actually going to create an error. And that's because when it jumps to R15, it's going to try and jump to 402010, which is empty. And it's also for data. It's not an instruction. So this is going to create some weird segmentation fault here. So what we want to do is we don't want to jump to the value at R15, we want to treat it like memory. Now you could put brackets around this and it would work, but let's use some more of the commands that we know already. So what we want to do is, first of all, R15 we know is pointing to the third slot. The way that we're designing our program is anytime you want to write to R15, you write and increment, but anytime you want to read, you decrement and then you read. So let's subtract from R15 the value of 8 to get it to the last written data, the last written address, or the last written slot here, the last written row. And then let's load now into RAX, which is just, again, our sort of our working register that just holds all temporary values that we want. And we're going to put in brackets R15. So we're moving to RAX, the address pointed to by R15. So again, we're going to look at R15, see this address here, and go ask RAM what's there. And it will look up and see that there's 0, but in this case, it's going to be subtracted first. So it's going to treat it as a pointer. So it's going to follow this like a roadmap. And then after that, we're going to jump now to RAX because that should hold the address. So let's test this out. Let's run through until we get down to print goodbye. So right now, R15 still pointed that empty slot we could see, 402010. So we're going to subtract. Now we're back at our last written address. That's great. And we're going to now move to RAX. This value, but we're not literally moving from R15. There's brackets around it. So we're going to visit this address in memory, and that's going to be right here. So we placed this value 401060 into RAX. So we have a handle on this memory address. We reversed what we did before. And now we can just jump to RAX, which will be 401060, which is this line of code here, resume hello. So if we step, we jumped back to resume hello. And now we're going to crash again because the code that we have here is bad. We're just trying to treat this as a literal address that we'll go to. So let's modify this again. And what do we want to do? Well, our practice to read, we decrement and then read. So let's subtract from R15 the value of 8. And then let's move to RAX. Whatever is at the memory that R15 is writing to. And then let's just jump to RAX. So let's try this out. Step through. Print goodbye shall return fine. Goes to resume hello. And now resume hello itself is looking at R15. And we know that it's at an address. This is, you could say it's blanked out. Now nothing is blanked out for you in something like assembly or even C. But we know this slot is no longer valid. It doesn't really matter what's written there. But we just know that our protocol is that when we're going to read a value from the call stack, we're going to subtract first and then grab the value. So that's what we do. We subtract. Now we're pointing to 402000. Then we grab that value into RAX, right? Using these brackets as a pointer. So 401021. That's in our RAX now. And then we can jump to that value. And now we're at resume here, which is our original destination. And we can jump now to exit. No need to save anything because we know we're exiting, but if we were not expecting to exit the program, we definitely would save our address and move it into the call stack. But now we could just get to exit where we'll tell the kernel that we want to exit our program. So we're asking him to terminate us. Very sad. We're zeroing out RDI with an exclusive OR operation. Don't need to understand this too much if you haven't seen it before, but it's just a very efficient way of making RDI 0, which the kernel is going to look at and report this value as our exit code. And then we're going to execute by calling the kernel, the system call, and telling him, hey, we're ready. We have our system call code put in for you so you know what we want to do. Previous videos go over this. And then we step through and then we exit with code 0. So really clean and effective here. So now let's use a real stack, right? We've been using this as a memory previewer, but we haven't actually used a stack. So there's two commands here that are going to sound very familiar and are very helpful. One of them is called call and the other is called return or RET. And those are built-in commands, hardwired in the CPU that provide the functionality that we just built ourselves. So let's start using them and then we'll talk about them a bit. We no longer need our stack, right? So let's destroy our stack, very sad. We can delete our starter pointer. Thank you, R15, for being our pointer. We don't need him anymore. We don't need to preview our fake stack anymore. We can get rid of him. And then we can get rid of look at the amount of lines of code here that we needed to keep track of our return addresses. We don't need that anymore. All we need to write here is call. So instead of jump, we're going to use call now. And what call is going to do is two things. It's going to put the address of our next instruction on the stack automatically. and then it's going to jump to print hello. So it does two things in one. It replaces our 3 lines of code or whatever we had with one very convenient instruction. And this is hardwired as well. So it's much faster than the way we were doing it. So now let's go down to print hello and follow our execution. We no longer need to store our return address for resume hello, right? In anticipation of us calling print goodbye. We don't need to manage the pointer to R15. We don't need to move it to memory. Don't need to do any of that stuff. All we just have to do now is put call print goodbye, and it will automatically go to this next position. Now, resume hello is also managing our old call stack where it's subtracting from our pointer, moving it to RAX and jumping to it. We don't need to do any of that. Now, all we have to do is type return, RET. Print goodbye, same thing. He executes, and he originally returned through our call stack management that we had, but we don't need to do that anymore. We could just put RET. Now it's worth pointing out, we no longer need to save this memory address because we had to manually keep track of where we were going to return. So we could just put return right after. And it looks a little bit confusing. These two have nothing to do with each other. This just so happens to be the end of print hello. If you want, you could put like a no operation here. And this is actually the return tied to this call if you want to look at it that way. We also don't need this one either, since we're no longer looking at this address ourselves. The call functionality will do it for us. So let's compile, unless I forgot something, and let's step through. So the first thing we're going to do is we're going to call print hello. So let's look at the stack here. This is the real stack. So when we step, look at that at the top of the stack, 401005. The address of this instruction here, which is jump to exit, 401005. So this is automatically done with this one instruction. So we called print hello. We're now in print hello. We step through. We're done with our system call. We print hello world, and now we're going to jump to print goodbye, right? Let's see what happens. And look at that. We have now our second address on top of the previous one. This stack looks a little bit weird because the stack goes from high memory to low memory. It's just the way it's laid out, but it's the same exact system. Instead of adding every time, you're actually subtracting addresses, and you do the reverse, but don't worry about it too much. As we dive deeper into the stack and using local variables, we'll have to tackle the direction of the stack, but it's not going to be a big deal, I promise you. So we have our two addresses here. We're now in print goodbye. We step through. We perform our system call. Here's our goodbye. And then we're going to return. And look at the stack. This top address is going to disappear as we return. It's going to pop it, we could say. And we jumped back, right, to this line of code, the no operation that we put here, call print goodbye, right after calling that next instruction. So we step through, we return now. And again, our next address is all lined up, ready to go. And you can see our stack pointer, right, is doing what R15 did before. It's pointing to what you'd say is the top of the stack. So we step and we've jumped back, right? That address is now gone off the stack. The reason why, by the way, that it's not on the stack anymore, it doesn't look like it, is that the stack pointer, this preview window of memory is shifting. So that data is actually still up here. We just can't see it because we're shifting our memory viewer. These instructions update the stack pointer the same way that we did with R15, but just automatically. So nothing is zeroed out. It's just hidden from view from us right now. And then we're back to our original starting point. We're at jump exit, and we can jump down to exit, and then we can exit the program with exit 0. So you see how much more convenient call and return are. So call, the right terminology is to say it pushes the return address onto the stack, and when we return, it pops it back out. Those are the two phrases that you're going to need to know. And there's actually two commands. One is called push and one is called pop. And those are very convenient ways of putting things on the stack. And we'll be using them in the near future. If you want to do some testing, you could just pop some values of a register like pop rex, let's say. I actually did that backwards. So it's going to put 01 into rex. You see 01 there and it disappeared off the stack. I really meant to push onto the stack, not pop, which push adds onto the stack. So if we push rex, it's all 0. So we could see that we added a slot of zeros, we could say, onto the stack. Why don't we push a value that starts out at a lot, like rdx? So let's push rdx as the first line of code here. You see how the stack is at the start? This slot just has a value of 01. So if we step, we've pushed this value rdx onto the stack for f, and then a bunch of f's, and then f7. So push and pop are very convenient. We'll use them as we get into more complicated programs pretty soon. I think that's it for me. But as always, I hope this was helpful. Thanks very much for watching. Thanks for hanging out with me. And I'll see you very soon when we move on to if statements and conditional jumps and condition evaluation in general. So I'll see you soon. Thanks again.